So, we start from where we stopped. We said that this is, you remember last time we discussed putting the initial condition in this one, if you recollect, we said that after Laplace transformation, this part I am just repeating the last what we said, Laplace transformation, this part becomes, the PDE becomes ODE. So, this we are calling as, this at t equals to 0, initial condition t x, initial time t equals to 0 is equals to 0. So, this term goes to 0 and we follow from there, we call this term Laplace transformation of t x t as theta. So, this becomes d square theta dx square s by alpha. This term is not there, simply this is theta. So, I am repeating this. So, this ODE would be solved by solving the auxiliary equation, d square is equals to s by alpha, d is equals to. So, the solution would be, solution of theta would be actually a e to the power under root s by alpha plus, right, and this was x plus b e to the power minus under root s by alpha x, right, solution of this one, because if you differentiate this twice, it will again come back to e to the power this term only, but twice differentiation will be, first time differentiate you will get under root s by alpha, second time you differentiate you will get s by alpha. So, that coefficient, coefficient was, it was d square theta dx square is equals to s by alpha theta. So, if you differentiate it, similarly minus e to the power minus, you differentiate it once, you will get minus s by alpha into e to the power under root s alpha x, and you differentiate it again, that minus s under root s by alpha will become plus. So, both are the solutions of this equation. So, the general solution is the sum of these two. This you get usually from the boundary condition, this you get usually from the boundary condition, right, this you get from the boundary condition. So, let us see how we go about it. So, we write this as plus minus p. So, this will be written in this manner, theta is equals to a and b we get from boundary conditions. When x equals to 0, theta 0 equals to a plus b. When x equals to 0, theta 0 is equals to a plus b, and that is what it is. And if I differentiate this, I get p a e to the power minus p x plus p b e to the power plus b x, because it was e to the power, I am just differentiating this theta. So, d theta dx will be a minus e to the power minus p x b p into e to the power p x, right. So, that is what I am writing here, that is what I am writing here. Now, k multiplied by this, k multiplied by this, k multiplied by this is nothing but Laplace transformation of k dt dx, k dt dx, that is right. So, that is nothing but Laplace transformation of the heat flux, Laplace transformation of the heat flux, we call it phi with a minus sign of course. So, we call it phi. So, first term is theta 0 at x equals to 0, I call it theta 0, theta 0 is equals to a plus b for x equals to 0 theta 0, and then I am defining phi, which is k minus k d theta dx. Thus, the minus sign comes because the heat flows from higher temperature, direction of heat flow, and from, if I higher it from lower temperature minus the gradient is negative. So, there is a negative sign comes k d theta dx. So, therefore, this is nothing but Laplace transformation of heat flux, and if I put this this one at x equals to 0, I call it phi 0. So, multiplied by this minus kPa, because this term will go to 1 and this term will also go to 1. So, therefore, kPb, this is how we can write. So, as a minus sign, this becomes plus and this becomes minus. So, I get theta 0 like that, putting two boundary condition, theta at x equals to 0, theta equals to theta 0, phi is equals to phi 0. What are the values of theta 0, phi 0? That we need not look into right now, but supposing the boundary values of temperature and heat flux is known, and I can take Laplace transformation of those, then this will be the from this. Now I can find out actually A and B, because there are two equations, two unknowns. So I can solve them, and I can find out B at any length L, because I have taken x equals to 0. So x equals to L I can find out, any value I can find out. So just I am trying to do that, find out, express A and B in terms of theta 0, phi 0. And what will you do in that case? Multiply this by Kp, right? Multiply this by Kp. So Kp theta 0 will be equals to Kpa plus Kpb, and if I sum this up, this term will cancel out, I will get A, right. Similarly, if I want to find out B, what will I do? I will multiply this by minus Kpa and add this up. So I will get another equation from which I will get B, and A will get eliminated, this term will get eliminated, and that is what I am doing next. That is what I am doing next, that is what I am doing next, right. So that would result in, let us do that then for you. So theta 0 Kp is equals to Kp A plus Kp, it was plus or minus, yes, Kpb, and phi is equals to minus Kpa, well, am I right? Minus Kpa plus Kpa minus Kpb. So plus Kpa minus Kpb. Add this up, so you will get Kp theta plus phi equals to Kp A, and therefore A is equals to simply half theta plus phi by, right. Similarly, if I subtract, repeat this process, I will get B equals to half theta minus phi by, that is it. So these are the two. So I get A and B like this, and this is what it is. This is what it is, A and B like this. So A is like this, B is like this, and I can put them back. I can put them back in the equation that I had. What I had? I had theta is equals to, what was it? A, right, Px plus B e to the power. So put A here, B here, put A here, B here, and similarly put for phi I can do the same thing, which will be Kp minus Kpa e to the power Px. So I can put this. Let's see. Let's do that. So if I do that, phi can be rewritten in terms of theta 0, phi 0. So let me just write it. Okay. So let me write it now. Right. This is what we saw. So A and B is like this, and I can write theta and phi in terms of. So if I write it, put A here, half theta 0, phi 0 by Kp plus half theta 0 minus e to the power minus Px here, e to the power plus Px here. Am I right? This is fine. This is B, this is A, this is A, this is B. I have just put them here. Similarly, okay, let us simplify this a little bit. Similarly, I can do for phi, but let us simplify it a little bit here. I isolate the terms of theta 0 and isolate the terms for phi 0. So this will be half theta 0, and from here comes half theta 0 again, and e to the power minus Px plus e to the power plus Px. And here half still remains, and I have phi 0 by Kp, and again e to the power minus Px minus e to the power Px, right. And what is this? This divided by 2, this term e to the power minus Px plus e to the power Px divided by 2 is nothing but cos hyperbolic px, cos hyperbolic ps. What about this by 2? Sin hyperbolic pa. So that's what we do. So you can see that theta can be expressed in this manner: half theta 0 cos hyperbolic px and plus half phi 0 by kp sin hyperbolic px. So let's write it that way, So this is what is written, replacing p using hyperbolic function. So I can write it like this: theta at x equals to s at any value, x equals to any value. So theta at x equals to at any value, and s because it's a function of Laplace transformation, so it's a function of s. T is gone, s has come. Cos hyperbolic s by alpha minus phi at x equals to 0, because phi 0 corresponds to x equals to 0, sin hyperbolic. So this is how it is. So we express, we have just written sin and cos hyperbolic, replace them, these terms, this including this including this by cos, and replace, got back the p again, under root SL. Now similarly I can do for phi. Let's see how do I do for phi, because phi was k d theta dx kp, this was the case. So I am just putting it here, kp half a, so phi 0 etc. e to the power px and kp theta 0. So again separate the theta 0 and phi 0 terms, and you will get something like this: phi is equals to kp half e to the power minus px e to the power px plus px theta 0, coefficient is theta 0 here. And similarly for this one you will have kp half e to the power minus px minus and minus, this will make it plus e to the power px. So this is minus e to the power px, and phi 0, so this is kp by kp theta 0 and phi 0 by kp I have taken. Now since there is a kp, both the cases there is a kp will cancel out and I'll be left with phi 0, because this kp divided by this kp and this kp divided by this kp and this kp divided by this kp. So I am trying to find out the coefficient of phi 0, so it will come something like this. So simple algebra, because if I expand it, kp theta 0 e to the power minus px by 2 minus kp theta 0 e to the power, this was minus px, this is px by 2. So this is common in both of them, separate it out, half, no, 2 you take this way and 2 you take this way, this is common. So if you do this, you get e to the power minus px, and this is what is this? Sin hyperbolic x, sin hyperbolic px, and this is what is this? This is cos hyperbolic px, So phi can be written as half minus half kp theta 0 sin hyperbolic x and plus half phi 0 cos hyperbolic x, right. So just writing this again using hyperbolic function, phi xs can be written as theta 0 k, this is p sin first term and then is the cos. So if I rewrite these two equations again, if I rewrite these two equations again, then I will get something like this: theta at any L, at any distance in a homogeneous isotropic material where k is not changing, and I am dealing with one dimensional unsteady state heat flow. I have not used any kind of boundary condition so far, only I said that is unsteady state. Initial condition I have used, that at t equals to 0 temperature is also equals to 0, and this is in terms of Laplace variable. So theta L s is equals to at x equals to 0 s, and similarly sin s L, this is what we got. And for phi I can write it like this: at any distance L, replacing x by L in both the cases, x by L, L, and this is coming because p was there, kpa, so replace p by s alpha, this is what I get. Now you can see that this can be written as 2 by 2 matrix in terms of theta 0 and phi 0, because these coefficients I can take it out, right. So, Laplace transformation of temperature at any distance L and the flux at any distance L can be written in terms of some constant which are actually part of the material constant, sectional constant, all these are, L is nothing but the length, alpha is the diffusivity, and of course, the Laplace variable is very much there. So, this can be, these are basically material, but this is the flux, Laplace transformation of flux and Laplace transformation of temperature. So, this can be written in matrix form. This we can write in matrix form, and we write it like this: theta L s phi L s is equals to some m1, m12, m21, m22. This I just write this in matrix form, phi 0, this I take it out, this is here. So, these are the coefficient of the matrix. This is so I can write in terms of boundary condition theta 0. In other words, I am now out of this, I am saying that theta at 0 and phi 0 is known. It can also be known that theta L can also be known, or phi L can be known. So, any two of them known out of these four. This is related to the length of the section, and K is thermal property, alpha is diffusivity, P is related to the frequency. P would be, P is basically, what was P? P is, P, what was P? P is S under root S by alpha. So, it's, not frequency, it is related to S. It is related to S and diffusivity. So, these are properties of essentially related to the material properties and Laplace variable, of course. So, M1, M22, if you can go back and see M1, see this value and this is same. So, M11 is equals to M22, M11 equals to M22, and these two are common, but there is some similarity. Here K, this is multiplied and here it is divided. So, I can write this expression for M11, 22, etc. So, M11 equals to M22, and this is what it is. M21 is this, there is a relationship between M12 and M22, but I can just let me write this full thing. M122 is sine hyperbolic this 1 by Kp, minus 1 by Kp. M21 is minus Kp. So, P is this, so sine hyperbolic this, right. Now, if you take the determinant of this matrix, you will find the determinant comes out to be 1, determinant, because it will come. We will just do that right now, because this will get multiplied by this, M11 will be multiplied by M22 minus M12 into M21, and this this will be, there are minus signs, two of them plus, and it remains minus. So, this will be cos hyperbolic, cos square hyperbolic, Px, if I may write this, and minus sin, which is equals to 1. So, determinant is 1, determinant of this matrix is 1, right, am I right? So, it makes sense. So, this can be written. So, this one we can write this, So, this is what it is, right. M11 minus M22 is equals to 1, So, determinant is equals to 1, right. Okay. So, now let us look at a construction. I have T and Q, and T and Q going out here at distance L1 and this is L2, right, layered section. I did it for a homogeneous isotropic single layer material, I said L. Now, I can extend this idea to layered section like we did for U value calculation. Here we can do the same thing for layered section. This is 0, L1, L2, etc., etc. So, like T0, Q0, T, TQ0, TQ, TL, QL1, and this is 1, L1, and this is TL2, T, and as a function of, so Q, flux here is Q, L2, T. So, at any time, but space wise this is how it is. So, this I can now write theta L1 S you know, I can write theta L1s Laplace transformation in terms of Laplace transformation, theta L1s, right, and phi L1s here can be written in terms of this, because we wrote it in terms of theta 0 and phi 0, phi 0. So, I can write it in terms of this. I can write it in terms of theta L1s phi L1s is equals to M11. I am putting a superscript now for the first layer. This is the superscript for first layer, right. So, theta 0 s, theta phi 0 s. Similarly, I can write now theta L2 s in terms of theta L1 s and L2 s. So, just that is what I am doing, L2 s phi L2 s, this is. So, each individual matrix if I know, I can find out. Now, replace this here, put this here, right, put this here, theta L1 s and phi L1 s, and this can be written like this, theta, you know, in terms of theta 0 phi 0, I can write it. So, if I have n layer, first layer will come here, second layer, third layer, nth layer, where this will be the Laplace transformation temperature at the nth layer, and this is a flux at nth layer, you know, because this is 2 layer I am showing 1, 2, 3, 4, 5, etc., etc. So, in fact, I can write it like this. Finally, I call it say A, B, C, D matrix, which could be a product of several matrices, where L is the overall thickness of the construction. So, I can write a ABCD matrix. Now, what will be ABCD matrix? It will be M11 n, M12, you know, all this nth matrix, then n minus 1th matrix up to first matrix, you know, last and then last. So, I can write it in this manner. So, that is the solution of matrix. This is a matrix form solution. Now, if I want to get the actual temperature and flux, I can, two of them being known, their Laplace transformation being known, I can find out them in terms of S and take inverse Laplace transform, and you get the temperature and, you know, heat flux at the other boundaries. So, that is possible. We really do not need that. ABCD is matrix of this kind. As I said, in the 2 there are n, there will be number of them, and one can find out this one, right. So, that is the kind of solution. Now I can treat the boundary in different manner. I showed you frequency domain treatment, where we said that we can separate it into number of harmonics. I am talking only of the fluctuating part, steady part I have already taken care of. So, it is a fluctuating part I am taking, you know, looking at, and basically I have not assumed any kind of, I mean, I can, one way is frequency domain, take sinusoidal boundary condition or cosinusoidal boundary condition as we have done. One can take even pulses, single pulse, like they do it in, you know, like signal processing and all. Take a pulse and find out the response of this pulse to the other side, right, transfer functions. So, anyway, we will do the simplest one in our class, but explain you some of them otherwise. Now, one thing remains, what about air layer? What about the air layer? You know, because we always said, we said that we have solid boundaries, maybe there is one layer, another layer, etc., third layer, but there will always be 2 boundary layers. So, I got to take care of this boundary layer like I did in case of u value. We did in case of u value, we take 1 by HO plus 1 by HI, etc., etc. So, I got to take care of that in some manner. Now, for air layer, thermal capacity of air is very small compared to the solids. So, I can assume rho c tending to 0. Therefore, k over rho c would tend to infinity, alpha. So, alpha, which is k over rho c, will be infinity. That is, thermal diffusivity is infinity. What does it mean? It will take very long time to diffuse, the heat to diffuse through such a layer, because storage is, you know, 0 storage, right. So, this is basically alpha is something like meter square per second. So, sorry, it will not store, allow instantaneously to go on. It will not take very long time, it will allow instantaneously to go. And followed by it is L s under root, you know, L under root s by alpha. This will also tend to 0. because alpha tends to 0, this tends to 0. Why this is needed? Because in my cos hyperbolic L, if you remember, A was nothing but cos hyperbolic under root S by alpha L. So, I want to find out this A for L layer, B for this L layer. Now, if this tends to 0, what will be value of limit this tending to 0? It will be 1, it will be 1, right. Cos 0, cos hyperbolic 0 also tends to 1. It is not very difficult to even derive. E to the power x plus e to the power minus x divided by 2 was the case, and you can expand this. E to the power x is 1 plus x square by factorial 2, etc., etc., and e to the power minus x is 1 minus x plus x square by factorial 2, etc., etc. So, if I have plus sign in this 2, this terms, all odd terms will cancel out, and this can be neglected, higher terms can be neglected. So, I will be left with 1. E to the power minus sin hyperbolic x, again you can show that it will tend to 0, because there is a minus sign involved here. So, so it will tend to 0. So, this tends to 1, and what about A, A12 or M12, I mean second term of the matrix which had sign hyperbolic, they will tend to 0. So, let us see, but there is a little bit of catch. So, M11, M12 will always tend to 1 for the air layer. For the boundary layer, this will be 1, because this tends to 0, this tends to 1. But M21, you see, remember this limit trigonometric function I am talking about, then I come to hyperbolic. Remember this sin theta by theta, theta tending to 0, what is the value of this? 1, because sin theta becomes nearly same as theta, and it is equals to 1. Similarly, I can show that sin hyperbolic, we can do that, because it was e to the power x minus e to the power minus x divided by 2, right, and I have now 1 plus x square by factorial 2, etc., anyway half is outside, and write 1 minus x plus x square by factorial 2, and then x cube, and so on, those terms. So, this will cancel out, and there is a minus sign here, sorry, there is a minus x remains, sorry, there is a minus sign here, because between them was a minus sign. So, this will cancel out, this will add up, 2x will add up. So, this is plus, this is minus. So, this minus, so this will also become minus, this is plus, because there is a minus sign in between, minus 1 plus. So, this will cancel out with this will remain. So, 2x by x will cancel out, divided by 2. So, again this will tend to sin hyperbolic, let me just do it again for you, sin hyperbolic x by x, right. This would be 1 plus x square by factorial 2, blah blah blah, minus 1 minus x plus x square by 2, right, and now this can be written as 1 plus x square by factorial 2 minus 1 plus x minus x square by factorial 2. So, this term will remain, and this will cancel out, leaving you 2x divided by x, it will remain 2 divided by 2, because half was there, so this is, there is a half here outside. So, this will tend to again 1. So, that is what I am saying, So, you can see that this term tends to 1, this term divided by M12 was something like this, there is a dividing term. So, S by alpha L, and I had k S by alpha. So, what I do is I multiply this by L, take 1 by k out, multiply this by L here, and divide by also L. So, this algebra is fine, I am just doing this. So, this will tend to now 1, and I will be left with minus L by k. What is L by k? L by k for the boundary layer is equivalent as h naught. So, 1 by h naught, L by k is equivalent to is a 1 over resistance, I mean sorry 1 over conductance, this is nothing but the resistance of the equivalent resistance of the boundary layer. So, that is how I write. So, 2 1 this tends to 0. So, therefore, for a boundary layer I can write like this for a air boundary layer 1 minus 1 by h, and if it is outside then 1 by h 0, if it is inside then this will be h I. Is it right? So, now I have got any homogeneous layer also will be 3 layered, 3 matrices minimum will be there, right. 3 matrices will always be there. So, you know nth layer was coming, how was it coming? Sorry, how was it coming if you recollect, how was it coming, if I recollect, go back there, you know. So, nth layer was here. So, one external extreme layer will be coming fast, which will be the outside, I mean inside. If the heat is coming from outside to inside, first layer will be the inside boundary layer, next will be the actual solid layer. If there are more than those layers, you will have to take them, and the last layer would be the outside boundary layer, because heat is flowing from outside to inside. If it is flowing from inside to outside, matrix will be different, it is not same, matrix will be different, because the product of those matrix also will not be same. Okay. So, so far so good. Let us follow it up from there a little bit more, right. Okay. So, we will go to the next one right now, next case where we will follow it up, right. Okay.